Nuclei emit three common types of radiation, distinguished partly by their penetrating power. An alpha particle can be stopped by a piece of paper. A beta particle is stopped by a small amount of aluminum, whereas a few centimeters of lead are required to completely halt gamma rays. An alpha particle is a helium nucleus. A beta particle may be either an electron or a positron. A gamma ray is a high-energy photon of electromagnetic radiation. An atomic nucleus, initially in an excited energy state, can emit a gamma ray directly in the way an excited electron in an atom makes a downward transition. In this radiation process, neither the atomic number Z nor the mass number A are changed for the nucleus. Beta decay occurs when a neutron decays into a proton, an electron, plus an antineutrino that conserves momentum and lepton number. Alternatively, a proton can decay into a neutron and positron plus a neutrino. The neutron or proton responsible for beta decay may be embedded within a nucleus at the time, in which case the beta particle is ejected from a nucleus. In electron decay, the atomic number is increased by 1 unit, and in positron decay, the atomic number is decreased by 1 unit. Following positron decay, the positron antimatter will quickly encounter an electron and the pair will annihilate, producing a pair of 0.511 MeV gamma rays. This energy corresponds to the rest energy of an electron or positron. When a gamma ray enters the sodium iodide crystal, it scatters off of electrons, which collide with atoms in its path, producing visible light photons. The visible light is collected by a phototube, and an electrical pulse is produced with a strength proportional to the energy of the original gamma ray. The gamma ray delivers its energy to the electron through the so-called Compton effect, where the gamma ray and electron collision is treated like a collision between two particles. The gamma ray scatters with a reduced energy and increased wavelength. The change in wavelength is given by h over mc times 1 minus cosine theta, where theta is the scattering angle. The scattered photon energy is thus E gamma prime equals hc over lambda prime, and is shown to be related to the original energy through the relation E gamma over 1 plus E gamma over mc squared times 1 minus cosine theta. The maximum amount of energy is given up by the gamma ray when it is completely backscattered by 180 degrees. In this case, the backscattered gamma ray has E gamma over 1 plus 2 E gamma over mc squared. The electron, on the other hand, receives a maximum amount of energy from the collision equal to the difference between the incoming and scattered photon energies. Here's a typical nuclear gamma ray spectrum. The original gamma rays emitted by the nucleus are observed as a peak with energy E gamma. At a much lower energy are the backscattered gamma rays. The scattered electrons produce the plateau of pulses that extends out to the so-called Compton edge, where the maximum kinetic energy of the Compton scattered electrons achieves its absolute maximum value from backscattered gamma rays. Nuclear spectra are obtained by placing a gamma ray source beneath the sodium iodide detector and collecting pulses for a period of time, in our experiment a couple of minutes for each spectrum. Here you can see counts building up in various energy bins with undetermined units called channels. A relatively uncomplicated gamma ray spectrum we will observe results from cesium-137 first decaying by beta decay into an excited state of barium. The excited barium nucleus then emits a gamma ray with an energy of about 0.662 MeV. Here's the cesium-137 spectrum with pulse counts plotted vertically and channel numbers horizontally. Note the large peak marked as E gamma. The smaller backscatter peak from these gamma rays is denoted as E gamma prime. The Compton edge is noted where the plateau of Compton scattered electrons quickly drops off. The sodium-22 nucleus decays by emitting a positron to produce excited neon, which emits 1.275 MeV gamma rays. The positron seeks out and annihilates an electron to produce 2 gamma rays with energies of 0.511 MeV. The peak seen to the far right is due to gamma rays emitted by the excited neon. It produces backscattering at the point marked as E gamma prime and a Compton edge just to the left of the original peak. In the middle of the spectrum is the 0.511 MeV peak due to pair annihilation. In this peak, you're seeing direct observational evidence for the existence of antimatter. The 0.511 MeV gamma rays produce a backscatter peak superimposed on the previous backscatter peak and its own Compton edge, just to the left of the 0.511 MeV peak. Cobalt-60, used in radiation therapy in hospitals, emits twin peaks of gamma rays at 1.17 MeV and 1.33 MeV in a two-step process. The two peaks are seen in the spectrum at the far right end and produce superimposed backscatter peaks and blurred Compton edges. To calibrate the energy scales of these spectra, we will assume that the two peaks in the sodium spectrum have known energy values and use these 2 points to calibrate all other energies. Right-click anywhere on the sodium spectrum and choose Energy Calibration, 2 points. Choose KeV as the energy unit. Click the cursor onto the peak at the far right and input the value 1275 keV. Click the cursor on the pair production peak in the center and input 511 keV. You may now measure backscatter peaks and Compton edges. The calibration on the sodium will also allow you to measure the energies of prominent features in the cesium-137 spectrum and the cobalt-60. Any dental X-ray technician will tell you of the importance of screening X-rays with lead shields. When gamma rays of intensity I0 enter an absorbing substance, the intensity of the beam is reduced as it proceeds through the thickness of material. The intensity drops off as an inverse exponential of the distance into the substance. The absorption coefficient determines the rate of decrease in intensity. A plot of intensity versus distance is expected to decay exponentially. The inverse of the absorption coefficient defines a characteristic penetration distance for the gamma rays. When the rays have traveled a distance equal to 1 over k, the intensity will drop by a factor of 1 over e to 37% of the initial value. This is analogous to the RC time constant in a discharging capacitor. We measure the thickness of the lead shields. We will be placing one at a time between the source and the detector. Begin with no shielding, add 1 lead shield, then 2, 3, 4, and possibly 5. Collect a cesium-137 spectrum for each amount of shielding and click on the gamma ray peak to determine the number of counts in the peak channel. Here the number of counts is 609, and the random statistical error in this type of measurement will be equal to the square root of 609. More shielding leads to fewer counts under the peak. Finally, with 5 lead shields in place, only 17 counts were obtained. Please note that with only 17 counts, the absolute error is smaller than it was with 609 counts. However, the relative error, or percentage of error, is much greater for only 17 counts. That is, the square root of 17 divided by 17 is a much larger fraction than the square root of 609 divided by 609. Plotting the number of counts versus shielding thickness in centimeters yields a decaying exponential, and a curve fit will determine the value of the absorption coefficient k. One can also plot the log of counts versus thickness, and fit a straight line with a slope equal to the negative of the absorption coefficient.